The least cost corridor. A corridor is something that defines for every cell in the output raster the minimum cost of traversing through that cell along the least cost path between two sources. For example, here on the right, we see we have two least cost paths. And these least cost paths are, of course, derived from a cost distance surface, where we start over here on the left with A as a source area, and from this particular cell as the destination back to the source. And then we create another cost distance raster on the right, and we have a source called B here. And again, we use the same cell. And from that same cell, we then compute the least cost path back to the source. So we end up here with two separate cost distance surfaces, where, let's say, cost distance surface 1 is the least accumulative cost for every cell back to the source A. And for number 2, every cell, like the cell in consideration here, represents the least accumulative cost back to source B. Now, when we put these together, here just showing one least cost path out of every cell that could possibly have a least cost path, when we put them together, we get something like this, where since we're using the same cells to compute back to B and back to A, then the least cost paths converge or connect for every possible least cost path on the combined surface. The surface is called the corridor surface or corridor raster. And every cell on the corridor raster, no matter which cell we have or choose, let's say we choose one here, it produces a value which is the least costly way of getting between A and B. Just like our original two here, if we join them, well, that path represents the least costly way to go from A to B. And no matter which cell we choose, that cell will find a path between A and B. And that's then called a corridor or a corridor raster. The corridor tool takes in two cost distance surfaces. One surface represents the cost or least accumulative cost to A, and the other, the least accumulative cost to B. So two cost distance surfaces must be input into corridor. So for example, here just A and B we'll say, we might have A stored in a variable called start, right there, and B stored in a variable called destination. Right here. To make the first cost distance surface, we just use cost distance with our start point, A, and then the total cost surface, cost. And that creates cost distance to A. Same for cost distance to B. Cost distance, our destination, which is B here, and then the total cost surface, which is the same for both of these. It must be the same to create a corridor. Once we have A and B, we put them into corridor. Pretty straightforward. A and B over here. And that creates a corridor raster, where every cell that you can choose is along a path between A and B, or start and destination. And that cell is on the least cost path between A and B, or start and destination. For example, we might say, okay, show us the corridor where the least accumulative cost is less than or equal to 2,800 cost units. And we'll store it here in AR. The result of that will be a Boolean layer because we're using a relational operation, less than equal to. So wherever AR, the output, is equal to 1, that means all those cells have the least accumulative cost of 2,800 cost distance units. Wherever it's 0, they don't. Here's an example using a threshold of 2,700 cost units between junction B and A, which was our start destination that we'd called them before. So our start point A and destination B. Here, the purple area represents the corridor within which no path will be greater than 2,700 cost units to go between A and B. And that then is called the least cost corridor. Because no matter where we choose a cell, that cell is along a least cost path between B and A. Likewise, any other place, it would be on a path that's least costly to go between B and A, staying within the purple region. Considering path distance now, path distance requires both a source and destination, as well as a total cost surface created in the normal way. So that's our T-cost surface from the previous examples, and a digital elevation model, so that the actual surface distance traversed can be taken into account with the cost, so it weights the cost values. So going to Python, to create the path distance, which is the same as cost distance, but taking into account the actual traversal distances due to relief, we're going to make two cost path layers. So the first one, I'll call it path distance from B to A, for example. And that will be equal to path distance and the source point, the cost raster, which is T-cost. And then the DEM. And there are many other arguments that you can customize to utilize this function. We're just utilizing it here in the most basic illustrative example that makes sense, using a DEM as the means to calculate the true distance traveled through relief. And there's the path distance layer. Next, I have to create a path backlink. So I'll call it path backlink from B to A, and that's equal to path backlink, and the same thing, source, our cost, T-cost, and our DEM. And that gives the same information as the regular cost direction or cost backlink raster. It just says which cell next to the one that I'm on currently is the one along the least cost path. Finally, once we have these two, we can create a least cost path from B to A. To create the least cost path, we use just plain old cost path, but now with these two rasters. So I'll say, I'll call this path P for path, for least cost path. And that will be cost path, and then the destination, which will be the from PT, that's point B. The cost distance raster, which in this case is path distance from B to A. And the path backlink, which is path backlink from B to A that we just created. Then the type of path we want, which will be single best, and the object ID to be carried over to the new path. So that's completed. So I'm going to close the Python window now and go back to the map to compare a least cost path, which is made from path distance, to the one we made from cost distance. First, I think I'll just turn off this one, some of these new ones that we made. Here, total cost, don't need it, trail 24. And then we go back to the last, which was path from B to A2 using that same cost surface. And you can see where the difference is here, especially right around here. So let's have a look at the total cost layer. That was the total cost layer here. And with the path distance, and I have to bring this layer up to the top as well so we can see both of them at the same time. There we go. So with this newer, taking into account the actual surface distance traveled that weights the actual cost layer, then we have a more direct route. Once we cross that water here, it provides a direct route, a more direct route to get to, again, the same path. So most of the path is the same, except that this area here is different. So once we weight the total cost by the surface distance traveled, it becomes more efficient to go along this straight line than it does to veer around here. And this one would be a better representation of trail modeling because it takes into account the actual distance traveled along the trail, which we didn't take into account with our original cost surfaces. And so that's a least cost path based on path distance rather than cost distance.